And I'm recording this session just so everyone knows. If folks continue to join, they can hop in. My name is Gina, and I am the program coordinator for the Climate Literacy and Energy Awareness Network. We really appreciate you joining us today. We have Tamara Ledley, who is our presenter today and our facilitator. She has been super involved with Clean from the start, and has this wonderful connection to the Climate Interactive En-ROADS Climate Solutions Workshop that she's going to lead for us, and she's done it tons of times. So she's an old pro, and what I'll be doing throughout this is I'll be monitoring the chat and the Q&A. So if you have any questions, feel free to put them in there, and I'll be watching that. And Tamara's going to lead us through some presentation and some interactive versions. So just stay tuned, and I'll let Tamara take it away. Thanks all for being here.
Okay, thank you. Thank you, Gina, and welcome everyone to the En-ROADS Climate Solutions Workshop. We're going to be using a decision support model called En-ROADS. En-ROADS stands for Energy Rapid Overview and Decision Support Model, and we're going to use this model today to explore the impact of various solutions to climate change to address rising temperatures. So we're going to go to the next slide here. So this model was developed by Climate Interactive, as Gina mentioned, in collaboration with MIT's Sustainability Initiative. So this is our brief agenda today. We're going to do a bit of an introduction, and then we're going to start exploring scenarios of success. And I will first get input from all of you as to solutions we should try, and through that mechanism, I will demonstrate how the model works, and then you'll get the opportunity to try out some solutions yourself directly in the model, and then bring them back to the full group to see if we can really keep the temperatures down and reach our goals. So let's just do first a brief introduction. So let's review the science and what's at stake. So many of you may know a lot of this information already, but just to make sure, I'm going to just review a little bit about atmospheric carbon dioxide, greenhouse gases, and its impact on temperatures and its impact on society. So this is a graph of atmospheric CO2. The scale along the bottom is years before the present, and the present is defined as 1950. The present here is on the right-hand side of this graph. So time does move from left to right. This is usually conventional, but it starts 800,000 years ago. And then the vertical scale is carbon dioxide concentration in parts per million. And you can see that the carbon dioxide has varied significantly over the past 800,000 years, but it has, until recently, it has not exceeded 300 parts per million. The minimum was about 170 parts per million, about 675,000 years ago. The high during these 100,000 year time scale was about 325,000 years ago here. And then here we have the present. And on this timeline scale, the amount of carbon dioxide in the atmosphere just goes straight up to here we are in 2019, 2022 now, but where the concentration of carbon dioxide is around 419 parts per million. So where does all that carbon dioxide come from? So this is a graph of on a different time scale. This goes from about 1850, basically pre-industrial period, up to about 2018. And we have here on the left, on the vertical axis, carbon dioxide emissions in gigatons of carbon dioxide per year. And you can see back in 1850, most of the emissions to the atmosphere were from land use changes, basically the clearing of forests for the planting of crops, agricultural activities. And that has pretty much gone a bit up and down over the course of these 170 years or so, but is not changed dramatically. However, here are all the other fossil fuels. We have in the late 1800s, coal became a significant source of energy, and that wedge has grown over time. to be where it is about today. It's kind of leveled off, maybe coming down a bit at about 14 or 15 gigatons of carbon dioxide per year. In the early 1900s, oil became a significant source of energy. And again, that has grown over time. Natural gas became a source of energy in around 1950, and again, has grown over time like the others. This gray area is other emissions, and the other emissions include emissions from cement production and gas flaring. Gas flaring is when there is natural gas that is brought up from the ground, and and when oil is extracted from the ground, gas tends to be one of the byproducts, and they burn it off, and then that puts that emissions into the atmosphere. Oops, I don't know why that happened. Okay, so but carbon dioxide isn't the only greenhouse gas. So this is a graph of the total annual greenhouse gas emissions by gas. The horizontal scale is the same, 1850 to about 2018. The vertical axis is a little bit different. It's greenhouse gas emissions in gigatons of carbon dioxide equivalents per year. The equivalence means is that these other gases that are added here, they put it on the same power of greenhouse gas absorption as carbon dioxide, so that you can put it on the same scale. So how much, for example, methane, if you had an equivalent, what would be the amount of carbon dioxide that you would need to get the same strength in its global warming potential as for methane? So here you can see that these wedges have grown. The carbon dioxide from fossil fuels from that last graph, 68% of all the greenhouse gas emissions are from those fossil fuels. The CO2 from land use and forestry is only about 7%, and that, as you can see, that green area is that light tan wedge strip from before, where it goes up and down a bit over time, but doesn't change dramatically. Then we have methane. Methane is comes from agricultural practices and from some industrial activities, as does nitrous oxide. So 18% of the greenhouse gas emissions are from methane, 5% from nitrous oxide, and just 2% from the F gases. The F gases are these man-made gases that were invented in the 1950s, some used for refrigerants, and when at sea level temperature and pressure, they were really inert in the atmosphere. But as they've gone higher into the atmosphere, they are very powerful greenhouse gas. It was a sort of a byproduct that was not really understood at the time that they were invented. Okay, so what does that impact of those greenhouse gases have on temperature? So these are two temperature records. Again, the horizontal scale is the same, 1850 to sometime past 2010. And here we have on the left, the vertical axis is temperature anomaly. Notice that this is not temperature, but a temperature change. And in this case, it is a change from the temperature in 1850. So you see here in 1850, that's 0. And so what was the difference in the temperature from 1850? And you can see that there's two records here. This red line here is the Hadley Meteorological Center in the UK. And the yellow line is the Goddard Institute for Space Studies in the United States. You can see that the records, while they're made up of different historical records way back here in the 1800s, the records move up and down pretty much in a very similar fashion to each other until you get to about 1970. 1970 is a time that we began to have weather satellites. And so after that point, when the records became much more consistent across these two data centers, the changes in temperature have been pretty much in lockstep. And so by around today, we've had an increase in temperature over 1850 of about 1 degree Celsius or 1.8 degrees Fahrenheit. So that's the historical aspect. What the models tell us is that if we continue on the current track, called a baseline case, where things are going to change pretty much as they have in the past, meaning that renewables will grow at the same rate that they have been growing, changes in use of coal and oil and natural gas will continue in those ways, as well as other cultural changes, economic changes, and innovation will continue at the same pace. The temperature by the year 2100 will be 3.6 degrees centigrade or 6.5 degrees Fahrenheit above pre-industrial levels or above 1850. But the Paris Agreement set our goals at least no more than 2 degrees C by 2100, and striving for no more than 1.5 degrees. And so that's these dotted lines here. And as we see, as we get to the model, that this will, that we will be shooting for a goal of getting this blue line, the current scenario, once we start implementing solutions, to come down and at least meet this higher dotted line of 2.0 degrees Celsius. Again, that's a change from pre-industrial levels to, and reaching for this goal of no more than 1.5 degrees Celsius. So if we have 3.6 degrees Celsius increase in temperature, that doesn't sound like a tremendous amount, but you have to think about this as a global average. And so what would an increase in temperatures of more than 3 degrees Celsius mean? Well, first of all, Arctic sea ice would be gone 2 out of every 3 summers. We've seen Arctic sea ice in the summer decrease dramatically over the past decade or so compared to previously. The Arctic sea ice always tended to recede from the Siberian coast. It always tended to be landlocked along the northern coast of Canada and Greenland. But that has decreased during the summer, so that only about in 2012, we had our last real minimum in September of 2012, where about 2/3 of the Arctic Ocean was covered with sea ice. And so, but if we have an increase of 3 degrees or more, 2 out of every 3 summers would be completely ice-free. This has significant implications for the absorption of solar radiation at the surface, because you move from a bright white surface, which reflects a lot of that solar radiation back out to space, to one of a dark surface in which would absorb 90% of the solar radiation hitting it. So that's a significant impact. In addition, 50% of insect species would lose over 50% of their habitat range. Since we are very dependent in agricultural industry on insects to pollinate the plants for agriculture, this could have a significant impact on food production. In addition, droughts would be 11 months longer on average than normal, than we see today, what I'm calling normal. And burn areas by summer wildfires in the Mediterranean could double compared to today. So we have lots of, we hear a lot about the summer wildfires out in the western part of the United States. These wildfires are getting bigger and occurring more regularly than they ever have in the past. So I'm going to show you another aspect of climate change that impacts especially coastal cities is sea level rise. So I'm going to show you a few maps here that show the impact of sea level rise. This is you can actually use this tool yourself. Here's the URL on the bottom here. Gina, if you want to put that into the chat, people might want to play with it. So here I have the global temperature rise is now 0. So it's at current conditions. And this is what Boston looks like today. And if we have a 3.5 degrees Celsius warming, so we've moved this lever from 0 to 3.5, that means that sea level has gone up 26 feet and is, or 7.9 meters. And you can see that all of this area is now underwater. So Boston which is usually the downtown area is in this little knob here, is this now reduced to this little highland area here. The airport is completely underwater. So there's significant impacts for Boston area, which is where I live. This is Amsterdam today. Amsterdam is part of the Netherlands, is in the Netherlands, where they have spent their, the generations holding back the sea from the north. But if we have an increase of 3.5 degrees, all of this area of the Netherlands would be underwater. And this is bringing it back to the United States. This is New York City today. Here is Manhattan, and New Jersey is over here on the left. And then the Bronx and the Queens part of New York is here on the right. I'll call your attention to this, the southern edge, the southern tip of Manhattan. This is where Wall Street is, and you'll see that that's relevant in a moment. But if we increase the temperatures there by 3.5 degrees, you can see that Manhattan Island becomes, the southern part of it becomes more than half covered with water. Brooklyn and Queens, New York are very much underwater. The New Jersey shore is also very much underwater. And here again is where Wall Street is. If we go to this next picture, this is Wall Street today. And I'll call your attention to this window over here and these two women walking by the window. You can see their heads are about halfway up the window. If we increase temperatures by 4 degrees Celsius, that water levels up 3/4 of the way up these windows. And so all the people here would be completely underwater. So you're talking about just where this location is, something on the order of a 5 to 6 foot increase, or even more increase in water. This is London with 4 degrees Celsius of warming. This is Parliament. See, the entire lower level of Parliament is underwater. This is the Thames River and the Westminster Bridge. The ends of the bridge are underwater. So climate-related disasters have cost the world over $650 billion just between 2016 and 2018. The damages associated with global warming, however, could cost the world over $54 trillion by the time we just reach 1.5 degrees Celsius, and we're at about 1 degree Celsius now. So let's explore some scenarios of success. How can we potentially stop that increase in temperature so that these dramatic impacts don't occur? So we're going to be using the En-ROADS model. This is basically the dashboard of the model. And we're going to go to that model in a second. Gina, you can put that URL in. We're going to link. You're going to get a link to a folder with the En-ROADS dashboard, and we'll talk about some of these the co-benefits and equity considerations of addressing climate change. First, I want to point out, so you can get that that document. I want you to notice this dashboard here. These are all the solutions that we'll be able to implement. On this left side here are the various types of energy supply: coal, oil, natural gas, bioenergy, renewable energy, nuclear energy. And this new zero carbon is imagining in the future that there is a new discovery that produces significant amounts of energy with very low cost and no carbon emissions. And so that's what this new zero is. And then carbon pricing. In this center section here, we have multiple categories. We have transport and buildings and industry, and in both of those, we could increase the energy efficiency of both of those, and we can increase the electrification of both of those using less fossil fuels. This bottom one here is growth. There is an assumption about how much population will grow over, between now and the year 2100. We can slow that growth, or we can increase that growth. And then there's economic growth. The extent to which the economies of the world grow. One other thing I want to point out is the model makes the assumption that all of these solutions that we might implement are implemented equally globally. So it's not like only one little town is going to be doing, but I'll be asking you to think about what the kinds of solutions that you have implemented yourselves, or your communities or your schools have implemented. But the assumption is when we put it in the model, the whole world is doing the same thing. This over here on this right-hand side, we have land and industry emissions. So on these are the other gases, the other greenhouse gases, other than the ones emitting carbon dioxide. So it's methane and nitrous oxide and those F gases. We have reducing deforestation here is another potential solution, and increasing afforestation, the planting of additional trees. And then this last one here is the technological removal of carbon from the atmosphere. So this model has been used quite extensively as of a few days ago, March 18th. These were the number of implementations of the use of the model around the world. There have been over 3,800 events reaching over 107,000 participants in 95 different countries. So it's it's a very useful model that is used extensively around the world. So we're going to go, okay, I've got a few other things here before we go to that actual, the En-ROADS dashboard. Let's go back to here. So one of the things I want you to notice is there's this tab here that's graphs, and I just wanted to show you some of the different kinds of things that you can look at. We'll be looking at some of these, but this is just an example of the kinds of things that you could look at when you implement solutions. How much of an impact does it have on all of these things? Well, the first one is temperature rise, which we'll be looking at quite extensively. We'll also be looking at sea level rise globally, but also sea level flood risk maps for various locations. Then a co-benefit is the impact of these solutions on air pollution. So for a certain amount of certain solutions, how much does it help address the issues of air pollution? How are the solutions you implemented affecting crop yield? So how much crop yield is decreasing based on different kinds of solutions? And then looking also at ocean acidification. You can also look at the population and the GDP, so the social cost of carbon or the reduction in GDP versus temperature, or the reduction in GDP from climate impacts. So this basically gets at the financial aspects of it. And then the last financial one is as actual cost of energy. As you implement these solutions, how does that impact the cost of energy? So this is the dashboard. This is the first document in that Google folder. And so remember now, I wanted you to spend some time looking at, this is the dashboard with all of those solutions. And the reason I gave you this document is we'll only be on this slide for 30 seconds or so. But this gives you an idea of what each of these levers means. If you move this lever for coal, you're discouraging or encouraging the mining of coal and the burning of it in power plants. If you have this new zero carbon, you're discovering a brand new cheap source of electricity that does not emit greenhouse gases. So economic growth, assume a higher or lower growth in goods and foods produced. And technological carbon removal from the atmosphere there are a lot of new technologies that are working on developing, being able to remove carbon dioxide from the atmosphere. There's a lot of them that work, but the real problem is scaling it to the scale that we actually need to address the global problem. So by having this document, you'll be able to look at these connections as we think through what the different solutions we might want to implement. So there's another aspect of addressing more than just by implementing the solutions. You can address more than just the climate change itself, the temperature changes. There's a lot of other kinds of advantages to implementing these solutions. Some of them impacting jobs and assets by having new technologies or moving people towards renewables or creating new jobs in those areas. Security of food and water, resilience of communities to be basically resilient to the impacts of climate change. Energy industry and mobility. How can people how do the solutions impact people's ability to get around? And then the connections of community, basically, how do people communicate with each other? And what are the benefits from implementing these solutions? And the last one here is the health and well-being and safety of society. So the second document that you have gives you some of these co-benefits for implementing the various solutions. And here, this is the same dashboard we had before. Here's energy supply with coal, oil, natural gas, etc. And each one of these gives you a little snippet of, by implementing that solution, what is it? What are the co-benefits? And the co-benefits are things that can happen immediately. Most of the solutions that we're going to be implementing are long-term solutions. meaning they have an impact over time, over the period between now and the year 2100. A lot of these solutions are ones that are immediate benefits. For if we tax coal, we're reducing air and water pollution, so we're improving community and ecosystem health. If we have a new zero carbon, research advancements in new technologies can create jobs, and there may be other useful applications. So I'm going to be asking you to think about what these co-benefits are when you implement solutions and when we implement the solutions in the model. The other consideration are the equity considerations. If we tax coal, like if we put a carbon price if we put a carbon price on, then fossil fuel workers risk losing their jobs, and the higher cost of the energy may be passed on to the communities. And if we have vulnerable communities that can't afford the higher prices of energy, we need to really think through how to address that. And so this slide gives you, and you have that document in that folder, to give you more of an idea of what the other kinds of equity considerations you have to take into account. So now we're going to move into really testing things out in the model. So I want you to think of what actions you can think of to help mitigate climate change. I want you and when we do that, I want you to, next slide. Why did it do that? I hit one button and it just goes way past. I want you to consider those near-term co-benefits of the proposals you're thinking. How can you address more than one problem with one action? And also, in what ways could the implementation of the policy harm vulnerable communities, and how you might address that? So we're going to go to the model now. And what I want you to do is so this is the model. And now this is the live model. So and I'll be giving you the link to this in a little bit. But as you scroll over different things, you can see, like, for example, this red line here is oil. It's oil in exajoules per year. It's about the amount of energy per year that oil provides. And by scrolling over, you can see what the numbers are for 1948, 2020, 2048, and 2049, and so forth. So we have here in the brown line here is coal. The red line here is oil. The blue line is natural gas. The green line is renewable energy. You can see that we're down here now, and there's not a lot, but it has an upward trend. The pink line is bioenergy. The light blue line is nuclear energy, and the orange line is the new zero energy. So it's a technology that's not been discovered yet. So on this graph, it is zero. This graph and all the graphs in the model go from the year 2000 to 2100, and we're here at 2022. And if you see this little kink here in the curve, that's COVID. That decrease in energy use was because of COVID. So you can see the impact of shutting down the entire world. That's how much it impacted the amount of energy use. On the right-hand side here, we have the net greenhouse gas emission. So again, this is in gigatons of carbon dioxide equivalent per year, very similar to that graph I showed you before, which included the carbon dioxide and the methane and nitrous oxide and F gases. And we have the black line is the baseline scenario, and the blue line is the current scenario. So here's the 3.6 and 6.5 degrees Fahrenheit. So I'm going to ask you now, how many people do we have here? We have about 10. All right, so Gina, can you allow people to speak? How will they raise their hands if they want to speak?
Yeah, raise your hand if you want to speak, and I can hit allow to talk, and then you should be able to unmute yourself and go ahead.
Okay, so think about what you do or what your community does, and then we can see what the impacts are if the entire world were to do a similar kind of activity. Or you can put it in the chat if you would prefer. But we need some of you to let us know. Anybody want to put something in the chat? What kind of things do you think would be impactful? What might get us? We are seeking to bring this number down to 2.0 at least, and hopefully to to 1.5. So we have reduced methane, we have, right, reduced methane, and everyone's using electric vehicles. Okay, so let's try a couple of those. We're going to reduce methane. And so we're going to just move that lever here, and you can see the extent to which methane impacts that increase in temperature. We've highly reduced methane and other gases here. We've gone from 3.6 to 3.4, and from 6.5 Fahrenheit to 6.0 Fahrenheit. So we've made some progress. Notice that the line really doesn't diverge all that much from the baseline until about 2030. And so we're sort of making a little progress. One thing I'll show you, let's focus on this this graph over here, and I can replay that change. And you can see that while there is, did anything on the left-hand side move? Since all of these are based on emissions of all of these use the exact same amount of energy, even if we reduce methane. And so there's been not a whole lot of impact on the global sources of primary energy. Okay, so somebody said increase, have electrification of transportation. So we're going to, and you said, we're not going to go all the way up to the end now. We're just going to increase, highly incentivize the electrification of vehicles. So having everybody using, or lots of people using electronic vehicles. Now let's see, we got down from 3.4 to 3.3, and we didn't come down a whole degree in degrees Fahrenheit. And if we replay this again, let's watch the left-hand side here, and I'll replay that. And what happens here is that you've brought down oil, the energy from oil, but in response to that, you had coal, natural gas, and renewable energy all increase. Let's play that again, because it is somewhat subtle. Basically, by electrifying transportation, you're decreasing the use of oil, but then people are moving to other energy sources as a result. And so that's why some of them go up. One thing I'll mention, that this model is what's called a systems dynamics model, which means that for each action, there are multiple effects, more than we could even comprehend if we just tried to think through them all ourselves. So the model does that for us. Okay, building efficiency is one here. So we're going to make the buildings more efficient. And for this one, I am going to click on these three dots here. So this is another level. We've been working so far is at a very high level. We can go and have more fine tuning of our solution. So here is the energy efficiency of new buildings and industry. And in this scenario, the baseline says that it's going to increase by 1.2% per year. And you can see this is this one here is the energy intensity for GDP. Again, this is the COVID blip. All right, so let's just see what happens if we double this. We're going to say from 1.2 to 2.4% per year. All right, so you got it down from 3.3 to 3.1. Let's replay that and look at the left-hand side here. And you can see by increasing energy efficiency, you're reducing the need for all sources of energy at the same time. And so the amount of energy from every single source goes down. But notice also that what we've been looking at is more out in the years 2060 to 2100. How much gets changed here in the 2020 to 2040 time range is almost next to nothing. And one of the things that I hadn't mentioned before, but when you put carbon dioxide in the atmosphere, it stays there a really long time, hundreds of years. And even at the end of 1,000 years, 20% of that carbon dioxide is still there. So if we put the carbon dioxide into the atmosphere, it's going to stay there a while. And that's why it doesn't have too much effect in these early years. You can also, in this particular scenario, you can change the start year. And then you can also impact the rate of buildings and industry retrofitting, meaning older buildings. Here it says 5% per year. So let's go up to 10% per year and see how that impacts things. You can see that that didn't really impact things very much at all. So let's just play this. This very, very subtle change. Okay, high carbon tax. All right, here's another one. We will go to carbon tax and then we'll explore further on this. We're going to go to carbon price and we're going to click again on these three dots and look at the more detailed possibilities here. Right now, the carbon price is $0 per ton. Anybody want to suggest an amount? When you say a high carbon tax, how much do you think we should put on carbon? Eric, you suggested this solution. How much per ton should we put? 50 to 100. All right, let's start with 50 and see how big of an impact that has. Thank you. That has a huge impact. It went from 3.1 to 2.7. That's the largest jump we've had in any one particular one. And this says that the year to it, so the start, we're going to leave the start year at 2022, but the years to achieve the initial carbon price, and then we can set a final carbon price. We can set the final carbon price to the $100 he suggested. And we'll leave it at that. That's interesting. It didn't have, by achieving the final carbon price of $100 per ton of CO2. Now let's replay that change. Well, it's only doing here. Let's, I should have replayed it before. Let's take this one out for a minute because I want to see what that impact is of. I shouldn't have done two right in a row, but let's try this. We're going to go back up and change this back to 0 and then change it to 50.
Glenn said, please adjust final price time frame to 2040. That's
Final price time. Okay, I'll do that. Let's just replay this one first. Notice how a lot of the renewable energies goes up. And because carbon pricing impacts oil, coal, and gas, it brings all three of those down. Coal being the most carbon intensive, oil being the next most carbon intensive, and natural gas being the third. So a suggestion was to change this year to 2040. Let's try that. We'll put the $100 here and we'll say 2040. So it brought us down another tenth of a degree. And let's see if we replay that. Again, it's the same scenario. All of the fossil fuels go down and renewables goes up. But notice here in the 2020 to 2050 timeframe, not much changes at all. The other thing that I wanted to show you is that you can find additional information. And this is where you can explore the equity considerations and the co-benefits. You click this little eye here. This gives you more information about implementing these solutions. What would it look like? What are the examples? What are the big messages and the key dynamics there? But also here you have the potential co-benefits from carbon pricing. So renewable energy becomes relatively cheaper, which can incentivize job creation in that sector. Reducing the use of fossil fuels improves air quality, increasing healthy, safe healthcare savings and increasing worker productivity. And in addition, you have the revenue from carbon pricing can be allocated to social programs that can be shared with everyone. Then you have those equity considerations here. The issue is that by pricing carbon, you're now making energy more expensive. And we can actually look at that. So let's see. I'm going to go to the graphs here. And actually, I think I can do it from here. Oh, here we go. Cost of energy. So you can see that we have cost of energy increases dramatically in these, by 2050, and then it kind of comes down a little bit, but it's still significantly higher. This is 29, almost $30 per gigajoule, whereas here it's $24 per gigajoule. So that's the cost of energy. So let's go back to this one. So you need to think through what do you do about people that can't afford that extra energy? And one possibility is to take the carbon tax and redistribute it as a dividend to those people that are most vulnerable and can't afford the additional energy. Okay, so those are the various tools I can show you. Let's just take a look at a few things so that you can like the impacts. We've looked at here's the temperature change over time, and you can see that this blue line is now diverged from the black line. It's approaching by 2100 the 2.0 line, but it's not really very close yet. There's still 0.6 of a degree high. What other things can we look at? We can look at sea level rise. And this is always a little bit scary, is that sea level rise goes from, with this solution, we're only at 2.6 to 0.71 meters of increase in global sea level to 0.61. So we're from 0.61 to 0.71. So we're only going down 1/10 of a meter. And that really doesn't diverge too much from the baseline until 2060. So there's still a significant amount of sea level rise that's occurring. If we want to look at a risk flood map. So does somebody want to suggest a city that we might look at? A city somewhere on the coast. This just takes into account sea level rise and not flooding from rivers and things that would be more inland. Does anybody want to suggest a coastal city that we should look at?
Hong Kong.
Hong Kong, okay. Okay, so what this map is showing you is that land that's still at risk is in the purple, and land that is saved from, if we had left this at 3.6, the land in green would be still at risk. But the land in green now, given the solutions we've implemented, would now be would have been saved by those actions. So Hong Kong itself is not too much impacted. This area over here still has significant risk. Anybody want to suggest another city?
Boston.
Boston. And so you can see that there are still a lot of this eastern part of Massachusetts. You save some of the land. Let's zoom in a bit. And this is the airport here. So the edges of the airport are still at risk by just decreasing it by this much. So that's another example. Let's look at some other impacts. I wanted to look at the air pollution from energy. Okay, and now here you can see that the impact on air pollution is significant and it's immediate. The PM 2.5, this is particulate matter that is 2.5 microns or less. That is the size particle that the EPA regulates, particles that are smaller than that. And you can see that the increase in the decrease in air pollution from particulate matter is significantly decreased. And then one other one I want to show you, actually, I'll show you a couple of others. Decrease in crop yields from temperatures. So this shows you that if you have the 3.6, the baseline scenario in 2100, then maize or corn would be, the crops would be reduced by 21%. By implementing the solutions we have so far, you're decreasing that decreasing crop yield to only 14%. So each one of these, you can see that the significant increase in crop yield for each of these different crops, given these solutions, but we're still not there yet. So what I want you to do now is I'm going to give you this in this upper right hand corner. I can copy this scenario and I'm going to put it in the chat. If I can find the chat, there it is. And so that I'm going to give you a few minutes to explore some solutions. Now I want you to leave the solutions that are already there and then try other solutions and try to find one that's of highest leverage. where if you implement that solution, you get the greatest decrease in temperatures. And then I'll give you maybe 5 to 7 minutes to play with it a bit. You can tell me if you want a little bit more time. And then we'll come back together and I'll have each one of you offer the solution that you discovered, and we'll see if collectively we can reach the goal of no more than 2.0 degrees C by 2100. Okay, so does everybody have, I'm assuming that everybody has the link. I sent it to everybody. So we're going to give about 5 minutes and then we'll check in with you. Is that okay?
Yeah, and feel free to continue putting questions in the chat if you have them.
Yes, you can ask questions orally or you can put them in the chat. I'll continue to watch the chat.
One question. So would bioenergy also include, like, if you're composting?
That's a good question. Let's go. So
Because
if
composting does
bioenergy is
reduce
produced from burning or combustion of living
living,
organic matter
right?
and solids. So this is
What
not
count?
composting.
Posting.
Composting is probably over here in the, that's an interesting question, but it might be over here in the methane and other gases. I'm not really sure.
Yeah, because I was
I'll
reading
have to
that
ask that
composting, yeah, composting helps remove methane from the atmosphere. But apparently, I'm in New York City, so the mayor decided they're not putting any more money into composting. So that was that.
Yeah. No, I can kind of see where that. So yeah, it doesn't say, it doesn't list composting here either. Okay, thank you very much, Chantal. How about, let's see, Jim?
Oh, I struggled with a lot of different things. I tried to up the renewables, thinking that upping the renewables was going to bring down the fossil fuels, but it didn't really see that much of a change. I've seen a little bit of this, but I've never had a chance to actually move the sliders myself. So the other thing that I tried was to increase the electrification of what I wanted to get into was the electrification of the, I'm sorry, the renewable generation of electricity. Where would I get that? Is that
Renewables right here.
renewables?
Yeah. And let's just go into the more details. So renewables, we're going to subsidize it by a certain amount, and you can and you can subsidize it starting a particular year, and you can stop it. So when would you?
Yeah, I'd like to start subsidize that right away. And I don't know
All right,
how
so it's
much.
2022, but how much would you like to subsidize it by per kilowatt hour? Let's see what this says.
So
You want to subsidize by $2 a kilowatt hour and see what that does?
sure, try it. Let's see what it says. Yeah.
Oh, I have to.
Good.
I guess it won't allow me. I guess it only allows you to do cents.
2 cents.
Okay, so there was an impact over here on the left, the energy sources. So renewables went up,
Okay.
but oil and natural gas went down. Or coal is already pretty low because we've stopped building new infrastructure. Again, let's
Right.
look at the years between 2020 and 2040. You can see renewables goes up in like late 2030s. The others
Right.
are, and natural gas goes down a little bit in the 2030s, but
Yeah.
there's not a real significant change, and there is no impact on temperature by
On
the
the
year
temperature, right.
2100.
Okay.
And this is interesting. Renewables primary is a primary energy demand. It goes up above the baseline, but then comes down below it. That's kind of interesting. Okay, thank you, Jim. Let's see, who else do we have here? John. John, do you have a solution to offer? Okay, well, Yin, you said that I see in the chat that you could not figure out how to do the mic. So you want to pick on economics because economic growth. Do you want to put in the chat how you want to change economic growth?
She should be able to either mute or unmute herself. Yes,
Yeah.
no?
So you did the 3 dots. So I'm asking you to put it in the chat. So I did the 3 dots. Now, what did you actually change? You would tell me which one you changed and how by how much? Did you increase or decrease the economic growth? That's basically everything put to the far left. All right, well, we'll see. So you slowed economic growth, the long-term economic growth from 1.5 to 0.5% per year. And the near-term economic growth from, what was it? 2.5 to 1.7% per year. Okay, and is there anything else? No. Okay, and so what did that do for us? It got us down to 2.1, so we're getting close here. From 2.2 to 2.1. And everything in that case comes down. Let's see what else we can look. What does the cost of energy do? Cost of energy doesn't, but let's see what energy demand does. Energy demand, that's what we're looking at here. And basically what's happening is because we're lowering economic growth, the demand for energy goes down. Okay, thank you. Carrie. Carrie or John, but either of you can either speak up or put in the chat what others, what other changes you might suggest. Okay, so we haven't heard from them, but what we're going to do now is we still want to get down to at least 2.1. So those of you that did offer solutions, what was a second solution that we could potentially add to this so that we can actually reach the goal?
One that seems to work is either reducing deforestation or adding afforestation.
Okay, so we'll do both of those here. That gets you down to the 2.0. One of the things to point out is that once you've implemented a lot of solutions, implementing more solutions has less of an impact because of the systems dynamics nature of the model. So if carbon pricing already impacts coal, then stopping building that infrastructure doesn't impact it quite as much as it would have if by itself. So we've gotten down to the 2.0 now. Let's see some of those impacts again. Let's first, we'll start off with the decrease in crop yield. So now we've gotten it down to 2.0. There's still decreases in crop yield, but they're significantly less than they were. Maize is, the decrease has gone down from 21% to only 10%, wheat from 17% to 8%. So it's better. It's still not great, but it's better. One other one, because I made a point about the Arctic sea ice earlier, probability of a summer of ice-free, ice-free Arctic. So this first one is the probability of an ice-free Arctic summer by 2050. And that went from 22% probability to only 11% probability. If you only go to 2.0, the probability of an ice-free summer by 2100 went from 97% to 19%. And if we had the probability of an ice-free Arctic summer at least once before the year 2100, we were absolutely going to reach that threshold in the original scenario, and it's only 80% chance now. So those are significant changes. Let's take a look at some others. Population exposed to sea level rise. So these numbers are still significant, but at risk to annual flooding, we go from 380 million people to only 353 million people, and living below high tide line. And this is significant because this is not just floods from a big storm. High tides happen twice a day. So when the sun and the moon are aligned right, you have super high tides. And And if sea level rise is such, that's the high tide on top of the sea level rise. And so there are still many people who are exposed to flooding due to high tides. Okay, let's look at sea level rise. So we got from 7.1 here to 6.1 before, and now we're at 5.6. So we haven't really improved things tremendously with respect to sea level rise. Let's see. Ocean acidification wasn't one we looked at before, but the historically oceans have been, this is the pH scale. The lower the number, the more acid the water is. And when you have acid in the water, it tends to dissolve the shells of marine life. So it's very, very bad for marine life health. Historically, the pH of ocean water has been between 8.1 and 8.2. And here with that business as usual, the baseline case, it went down to 7.83. And now we've held it down at 8. One thing to point out is that this scale here is logarithmic, not linear. And so those are significant changes. So a change from 7 to 8 is an order of magnitude. So this is not just a factor of 3% or something. This is a matter of more like on the order of 50%. Yeah.
I have a question. So does that
Yeah.
take into account the fact that we are going to have less fossil fuels because it's not staying around? I mean, we have used so much of it already, no?
There's still enough fossil fuels to last. Well, I mean, I think that I think there's still enough fossil fuels that in the timeframes that we're looking at, I don't
Okay.
think that that's as much of an issue.
Hmm.
It will become more expensive to extract those fossil fuels as time goes on. That's true. So the cost of energy will go up.
So right now we're just managing the damage.
Well, the thing
No
is,
longer, if
let's
we
see,
don't
what
do
else can we
anything.
implement to try to get this down to 1.5? We've looked at some of the impacts when we've gotten down to just 2.0. So what else do we have to do? What other things should we try to get this down to 1.5? We've
Keep it
stopped
popular.
building coal infrastructure. How about if we stop building oil infrastructure? Okay, so now you've
Ooh.
brought that red line down to close to 0, and you've gotten this down to 1.9. So that's not a tremendous decrease anymore. So what else is still high? We want to get these things down early, and then the one other fossil fuel that's still emitting is really way up here is natural gas.
Right.
So what should we do about natural gas?
We should, first of all, stop subsidizing it.
Okay. We're going to tax it. All right. It didn't
Yeah.
change the temperature. By taxing it, it didn't change the temperature all that much. And if we replay this, you can see that this increase here, all of these, the natural gas increased here because the other sources of fossil fuel energy, coal and oil, went down. So
Right.
a lot of it was transferred, a lot of that usage was transferred to natural gas. So if we tax it, it comes down some. What else should we try to do here? We can just reduce oil, gas utilization. We want to try to change that by 50%. That
Cool.
just is down to 1.8. It still doesn't get us there. Okay, so let's try some other things here. Wait, right now we have renewables as taxed. Did we do that by mistake? We taxed it. Let's say
Yeah, we wanted a subsidy.
we wanted to subsidize it, yeah. So that had to be the minus. Okay, so it's still, even at that, we
Still didn't change it.
subsidize it, it's still 1.8 here. That didn't change the temperature at all. Interesting. Okay, what else do we need to try? What haven't we done yet? We haven't done energy efficiency for transport, and we haven't
building
electrified buildings.
Right. That
So which one should
definitely
we
is
try
something that
first?
we should be working at. Yes, electrifying buildings.
That didn't do much. Let's get it up here. Okay, anything else people would like to suggest?
Reduce
Okay, well-
methane a bit more.
We can do methane a bit more. Let's highly reduce it. So we've got it down to 1.6. All right, so let's
Where do we end up on carbon price?
look at that. Price of energy. So it initially goes way up and then comes down below what the baseline scenario would be. So over time, the cost of energy actually decreases once these initial additional costs go away. So that's interesting. We've not invented any new zero carbon technology, but you saw the price of energy went way down, but it didn't impact the temperature all that much. Okay, so we're getting close to our time here, so I just wanted to finish up these slides.
And Ian just said in the chat, do something to reduce oil and coal.
Reduce oil and coal. Okay, so we stopped building oil and coal infrastructure. There is one that says utilization of coal reduction. So we're gonna change this by 50%. We're gonna reduce the utilization of coal by 50% starting right now, the year 2022. Okay, so that had an impact. Let's go back to this here, sources of energy demand. So now that brown line, which was up here, we stopped using it. So it's gone down, and we can do the same thing for oil. We can reduce that by 50%. Okay, it still didn't impact the temperatures anymore. Okay, so this is a scenario we've come up with. There are, and as one of you noticed early on, there's not one solution. You have multiple solutions. This Climate Interactive says there's no silver bullet, but there's silver buckshot. All of these things have to happen together. So let's just finish up by going back to the slides. And
I was wondering about population. I guess if you try to keep that constant, would that help?
I don't think you're going to be able to get it constant, but you can lower the growth.
So with the growth,
And that got us down to the 1.5. All right, so now that we're down at 1.5, let's see what that does to sea level rise. So you've got your biggest change here. It's still a half a meter as opposed to 0.71 meters. It's still half a meter. And keep in mind that this is just by the year 2100. Sea level will continue to rise after this. And that's why those sea level rise maps that I showed you at the beginning for New York and Boston and Amsterdam had what was 7.9 meters and 26 feet, was because it was a long-term equilibrium level of sea level rise, not just by the year 2100.
Have they calculated a scenario where, you know, with the suite of all these things where it's perfect, like to really do it, or it's like, as the computer done something like that?
Well, so
like the optimum.
basically, when you say when we do it, what do you actually mean? Do we get, we now have gotten the temperature down to no more than 1.5 degrees increase by the year 2100.
Mhm.
But that doesn't mean that you've stopped the climate from changing. And because carbon dioxide is in the air and continue to be over time, and a lot of the changes are basically baked into the system already. That
Oh, no, yeah, I understand that. I was just wondering whether if they ran the model and there were optimum numbers for all those things, like we were playing around with them, but did they figure out a combination?
Actually, there, one of the things you can demonstrate with the model, and I did do this in a paper I presented in December, is there are multiple ways of getting to this goal. You can do all the things to impact the fossil fuel industry and do nothing else and get to the goal. or you cannot touch anything of the fossil fuels and implement all the other solutions and also get to the goal. However, what we haven't really talked about in any depth is those equity considerations and the co-benefits. What are the most beneficial short term? One of the problems in the in politically being able to implement these solutions, what is the political feasibility of a lot of these solutions? You see, we keep coming up against roadblocks because of politics. The policies don't get put into place. And so it becomes really difficult to address those kinds of issues. What are the political realities of implementing these solutions? And as I said before, different solutions will work better in different places. But my view is that you're going to have to, we need to try to keep the carbon dioxide out of the atmosphere so that we can control these temperatures over time. But society will have to address the impacts of climate change for whatever those impacts, however those impacts manifest themselves in their particular location. In some places, it'll be extreme events like large precipitation events that cause flooding, whether or not they're on the coast. Some of them will be extended droughts and the resulting wildfires. And how do you make your community, your region more resilient to those kinds of changes? Those are the kinds of questions that also need to be asked. So it's really going to need society to act on both fronts to mitigate climate change, mitigate those changes, as well as adapt to the changes that are coming. So just, I wanted, because these, I don't know why this is not. Okay, so we've kind of gone through a lot of this already. What I wanted to do is just since we're at the end of our time, this is about carbon pricing around the world. Only 22% of the carbon pricing plans that are in place or planned actually cover the global emissions. And you can see the United States has very big areas where there has been no carbon pricing put in place, and that's a political issue. But I wanted to get at what you could do. And so as we talked about, all your individual efforts really by themselves don't account to much. They're very, very small. However, by your doing this yourself and communicating to your students, you begin to influence larger and larger social networks and larger organizational networks. I teach global climate change to undergraduate business students. I work to help them understand that their organizations are going to have to address climate change issues. Your students, in whatever careers they ultimately choose, are going to have to consider how climate change impacts their community, as well as how they impact, the organizations impact climate change. And so ultimately, at this public level, creating the laws creating the laws that will be implemented in order to address these issues has to happen. But you need really to build that political will in society at large. And then ultimately address cultural norms. The one other piece I wanted to show you, because all of you are teachers, is the student assignment. Now we've gone through, that's not what I was supposed to get to. Oh, here's a student assignment. So I've run this workshop for you, and you can have somebody run the workshop for your class. I've done it for high school groups and for some middle school groups also. But there are assignments that you could give to your class. The shorter version I did use in my class one time. And basically what this is it gives you a 20-minute video that shows the students how the model works. And then they can, let's see, it's going to come up. I didn't download this ahead of time, so it's going to take a second. It's not opening for me. Where is, oh wait, it opened over here. I will move it over here. Okay. Let's make this bigger. I don't know. Pew. So hopefully you can read that now. So here's a link. You open the En-ROADS model and you can review that control panel and then that introductory video. The introductory video allows you to, gives you basically that how the model works kind of demonstration. Then you go in and you develop a scenario. So your students could either in groups or individually develop a scenario that gets them down to 2.0 degrees C by the year 2100, and then answer these questions. So this one just this plan, but then getting the students to think about the political feasibility of that plan. So getting it, having your students help them think through how they can address this larger issue in terms of scaling the number of people that actually care about this. This next question, the winners and losers. This gets at the equity considerations. Who really loses in the scenario that's been created, and how might you address that? What are the surprises that came in you saw when you created the scenario? And this gets at understanding that there's not one solution that's going to work, and also understanding that it's a systems dynamics model. One of the things you can demonstrate is that if you go through and you implement each individual solution by itself and see how much of an impact it has on climate, on the temperatures by 2100, and then you add all of them together, you'll see that some of the individual impact solutions are not, it's not additive, it's much less, because once you've impacted a certain industry, so if you've impacted one solution, the amount of coal that gets used, then the next solution won't be impacting it quite to the same degree. So this gets at having students understand that systems dynamics nature of the Earth system. And then hope, and this gets at a lot of the questions that all of you had. What is it that you can hope to do, or what is it that's possible to help society survive and thrive? And then getting down to these personal actions. What can you do personally? And my best suggestion for that, especially for the youth, and that goes back to this other slide here, which I'm going to go back to. This one here, the global climate strikes. Youth played a tremendous role in these global climate strikes. They're the voice of the future leaders of the world. And they are starting to have much more of a voice. So helping your students contribute to that voice and take up action within your communities, within your schools, within your communities, and ultimately your state, the country, and the world. So I will end with that. I think I have this has my email address. If you have any questions, you can visit Climate Interactive and see more about the model itself, access that student assignment. There is the longer assignment you might have seen there next to the short one. That the short one can be done in a class period. The longer one is more like a project that would be over multiple days or weeks. And it gets much more in depth into those equity considerations and those co-benefits. So thank you very much. And are there any questions?
Thanks, Tamara. Chantal, you have a question?
Yeah, I wanted to ask, I guess for the economic growth, so will the model be considering such things as COVID, like a pandemic, or even war, for example? What can happen? Is that be part of the model? And you mentioned that who's losing. To me, it seems like the animals are the ones really losing. I was looking at the model.
The model doesn't talk about the animals, but yes, the animals are definitely an issue. In terms of, what was the first question you asked?
Oh, I was asking whether
COVID.
the model considers, like any like
so one of the
pandemic
things I can
or
show you,
wars.
let's change this back to green primary sources of energy. What was the impacts? I have to remember which graph it is. Carbon dioxide, greenhouse gas concentration. Right, if I go over here in this one, well, it doesn't have that. Greenhouse gas concentration. Oh, that's not it. There was one that maybe it was carbon dioxide concentration. Let's see. That's impacts CO2 concentration. No, there was one in which there was a red dot. If you implemented, it showed where the Glasgow commitments to carbon dioxide removal or greenhouse gas removals, and the part of it was to get to get the scenarios to go below that line. In terms of COVID, that's really I don't want to actually. Why don't we just go to a new version of the model because I can pull it up from there. Okay, so this is the net greenhouse gas emission. You see that dip right there?
Mhm.
That's the actual measured dip in the carbon dioxide or greenhouse gas emissions because of COVID. It doesn't take COVID into account directly in terms of, I mean, the only way you would do that is like, can you implement a global pandemic? But you would have to do that through a scenario of things. So like, what was the impact of the pandemic on coal and oil and natural gas usage? What was, and methane. So all the other things wouldn't be impacted by the pandemic. Energy efficiency is what it is, whether you have a pandemic or not, whether or not the transportation is electrified. Population growth might be impacted because of the pandemic. So you could come up with a scenario, a suite of solutions that you think would represent what would happen in the case of a pandemic and implement those solutions. But there's no lever to say what would happen
Okay,
by just implementing, by just having a pandemic occur. Are there any other questions?
thank you.
Okay, well, thank you very much, and I hope you have a good evening. If you have any other further questions, you can email me, and I will. If I can't answer them myself, I can find out the answers.
Thanks so much, Tamara, and thanks everyone for being really engaged. This was a super interesting discussion, and we appreciate you being here. So, and yes,
Very
thanks
much
again.
appreciate you
Tamara.
being here.
Yeah, definitely. Let us know if you have any questions. And have a good evening.
Okay, thank you very much.
Thanks all. I think I'm just gonna end the webinar for everyone, if that's okay.
Okay. Thank you,
And,
Katie. Gina.
all good. I'll talk to you later. Thanks for
Okay,
everything.
bye.
Bye.